Hi, Journey team. Today we're going to continue talking about our longitudinal waves. And I feel as though yesterday, teaching you about longitudinal waves and compressions and rarefactions that are moving along with the energy was kind of an easy baby step in learning about the longitudinal waves. Today we're going to talk about how different sounds are made with those compressions and rarefactions that are hitting your eardrum. And I want to just start by reminding you that our I can statement for today is explaining how the vibration of particles in the air and other materials results in the transfer of energy through sound waves. The key idea here is that you should be able to draw particles as they move in compressions and rarefactions from the point where the sound is coming from all the way to the eardrum. Now, I saved some time today because I didn't want to spend I don't know, 5 minutes drawing particles that had compressions all over it. So I grouped together my particles into solid lines instead. And the purpose of me drawing this longitudinal wave is because once we start measuring the sounds and talking about high notes and low notes and loud amplitude, we have to look at these waves a little bit differently. Um, Showing waves as compressions and rarefactions when they're measured is actually translated into a picture that is a transverse wave. I know it's interesting that they do this, but it's one way for us to show how large or how loud something is. You can't really show that movement from the resting line if it's a compression. And so the common practice is to change the shape of it into a transverse wave. So what I'm going to do here is I'm going to show you how it looks. If each one of these is a compression and between them is a rarefaction, and excuse me, I know how hard it is to use these the touchpad for making this. I don't have a mouse that my mouse doesn't work very well, so I'm using the touchpad like many of you are. I'm going to show a crest. Actually, maybe I would go opposite and go with a trough on each of these. Let me go back to the pencil. So I'm going to show a trough on the rarefaction and a crest on the compression. Trough, crest, trough, crest. Okay, so you kind of get the idea that how it's being measured is its size is now being indicated as a transverse wave. And this is only for us to map out the the strength of the compressions and the size of the compressions when they hit our eardrum. A transverse wave is never how a sound wave is hitting our eardrum. You see that ending is pretty smooth right there. But a transverse wave is a way for us to measure and show how many decibels something is hitting an eardrum by, the amplitude, and so on and so forth. So I'm actually going to be talking about sound waves, but I'm going to use some transverse waves to show them. Oh, if you're wondering how to draw this, um, you don't have to draw these waves here. I just wanted to show it to you in this video so that you knew what to do for in this in this next slide. Okay, let's start with the first word that we've already heard of. Last week we heard the word frequency. Actually, it was the week before that when I was introducing transverse waves. Frequency, when we talk about sound, is referring to pitch. So frequency is how many waves are occurring per second. And when we hit a high pitch, there's actually many more waves that are hitting a location per second. And so we have a very high pitch or high note. And one way, as proof for you to understand that high frequency in sound means high pitch, is that you can actually feel how fast how fast longitudinal waves are hitting a place by putting your hand on your vocal cords on the front of your throat when you are talking. If you hit the high notes, it's going to feel very smooth because there are so many compressions that are moving through the tissue there that reaches your fingers to touch them. High notes, music's high voice, piccolo, and how it would look, you're going to see a lot of compressions hitting per that moment of time. If you want to hear how high pitch sounds, you can click on the audio and listen to that. Low frequency sound, low music notes, low deep voice, tuba. Now, I really do emphasize put your fingers, your three fingers, three middle fingers holding up the number three with your hand, put them on the front of your vocal cords on your throat and make a really low sound. And you're going to notice that the vibrations are very slow and not very many of them are happening. Some of you can get down to that really low. It sounds like frogs when you get really low and you can kind of slow it down. You can feel that slow down and that vibration that's happening on the front of your throat. But enough of that. Frequency is about pitch. If it's high frequency, it sounds really high. If it's a low frequency, it sounds really low and really deep. I tend to use my voice to mimic that as I talk about it. So I apologize. Let's talk about amplitude though. Amplitude is how loud something is. If something is really loud, we are going to see those compressions are moving way off their resting point. They get pushed way out of their resting point and then they have to come way back. It causes a lot of damage. And sound waves moving through the ground, you would notice more particles are moved out of place if that's happening. When we look at amplitude of sound waves and they have a high amplitude, we're going to see this really high ups and downs. I tried to keep the same number of crests and troughs in this transverse wave, but show that something that's really quiet has a low amplitude. I used a tuning fork for mimicking loud and quiet because the tuning fork keeps the exact same frequency. This one is the G note. And so when that frequency is struck hard, you have a loud amplitude, but it's the exact same note. When I hit it, tapped it very lightly, it was very quiet, but it's still that exact same high note. So I wanted to make sure that you're paying attention to that. Okay, now this is informational purposes. When we talk about how fast sounds can reach from one point to another, we're talking about wave speed. Have you ever noticed that at a track meet, when they start a race on the other side of a field, they need a gun smoke from a cap gun to show when the race started. Because if we rely on sound to travel through air across a football field or a track, as we would see that in the, let's say the 200-meter run, we would be slow in starting the stopwatches if we were starting them from the other side of the field. So we have to rely on sight because light travels much faster than sound does when it's moving through air. Now, why is this? As we look through this table, air, the particles are spread apart, so far apart that the energy takes longer for the sound to pass through it. And so air is the slowest of the three phases of matter. When we move into liquids, sound travels faster, obviously, through liquid than air. This is because those particles are closer together, but they're not locked in their pattern. And so they still are not as fast as how sound would travel through solids. Sounds travel fastest through solids because particles are close and can transfer energy at a quicker rate, the quickest rate of all. And so there are age-old stories about how putting your ear to the ground would tell you if a herd of buffalo is coming. Putting your ear to a train, you could hear trains for miles because those are solid materials and those sounds can pass through them. So what I'm leading up to here is I am going to switch over to this is what we're going to put in with Edpuzzle. The Blue Man Group, it's one of my favorite entertainment groups to go and see. If you ever get a chance of this someday, you want to go and see them. They use different shapes and sizes of instruments in order to create different sounds. Now, when we have different sounds that are occurring, we simply can make the instrument smaller or larger or wider or narrower, or we can hit it harder in order to cause all the different sounds to come out of it. And so I don't want to give too much away, but the Blue Man Group and the Edpuzzle is pretty cool in answering those questions about, how did they make the high sounds? How did they make the low sounds? Please go back to your Pear Deck notes if you need help in understanding what was happening there and answering those questions for Edpuzzle. And that concludes our lesson for today. Have a wonderful day, you guys. I'm excited to throw out some choices tomorrow for wave activities for you to share and come back and present to us in what you did. That will be coming up tomorrow for Wednesday. All right. We'll talk to you later, guys.